All right, next speaker, CEO of Cognivue. Put your hands together for Morris Simon. Take it away.
All right, good afternoon, ladies and gentlemen. My name is Simon Morris. I'm the CEO of Cognivue Corporation, and probably the smallest company presenting today. 25 full-time people and about half a dozen part-timers. But we've developed a very innovative process of technology designed to enable high-performance vision processing, but cost-effectively and power-effectively compared to today's technologies. We actually naively went after automotive safety vision first. We launched a company in 2010, and surprisingly enough, got amazing traction very quickly in the automotive market, doing things that basically incumbent technologies couldn't do, delivering very high-performance vision in power-constrained implementations. In the automotive market, the power constraint actually had to do with dissipation, that the heat generated by the processors that were next to the sensors was too great and basically challenged the algorithm to see through the noise, especially at nighttime. So the camera, of course, at nighttime needs to see, and more importantly, the algorithms that are running in the background doing object detection, like detecting the boy behind the bumper there, also has to see through that noise. So the heat is actually a key issue. You got to keep the heat away from the sensor. And then more recently, we've started to expand into wearables, consumer applications, where finally, and interestingly enough, some of the stuff that the automotive market's doing in terms of leading the adoption of intelligent vision processing is actually coming into consumer products. So I'll talk about that in the next set of slides. By the way, how much time do I actually have? Because I know I think the session ends at 4. Okay. I've got a few slides here, and I think it's going to take me more than 2 minutes. So the Internet of Things, or wearable devices, are full of sensors. We've heard about some of that today, including audio sensors, MEMS-based sensors. And really, though, there's what Jeff Beard talked about, is that one of the most valuable sensors is still missing, and that's the ability to see. And why is that? Well, actually, Jeff talked about the fact that there's huge amounts of processing power required to do vision, and you take it for granted because we have vision. So we don't realize how difficult it actually is to interpret your environment through your eyes. And the challenge, of course, technically, actually, is in most products is that there's either a heat dissipation issue, as I described earlier in the automotive market, which actually also affects some of the consumer products, battery life issue, and of course, cost effectiveness. So certainly there's compute power out there that can do very sophisticated vision processing, but it fits into the trunk of a car rather than in a small cube camera. So the gap then in vision is being really around performance per power. And to give you an example, you could get maybe out of Google Glass less than about an hour of video with the glasses on, and there's no vision processing. You've got kind of augmented reality there with a sort of heads-up display, and you can record video, but you've really only got about an hour's worth of battery life out of it. So you need a substantial improvement in performance per power to make a product like a smart vision glassware product power and cost effective. And the performance issue, again, has to do with the fact that the incumbent technologies that are out there are really, you might have the performance, but again, it's too costly to actually do what you need to do. So as an example, you might today be able to do best case about VGA resolution, but actually the products that need to appear in the market, or are going to appear in the market in a few years, are going to be doing 1080p, 60 frames a second stereo. So if you look at augmented reality, and this is the processing required for augmented reality, where what I'm talking about here is actually is recognizing objects and doing something with the fact that you've recognized objects in the real world and merging some graphic with it, or vice versa. You might be merging a graphic on top of the real-time video. This augmented reality processing flow, let's say with glasses, the key part of that pipeline of processing is this tracking function, where you identifying an object and identifying an object in the real world and trying to paint it in the graphics. That processing path takes about 50 milliseconds to be real time. So for the time you acquire the image to the time it goes on a display, or by the time you actually want to do something with that, you got about 50 milliseconds. With an iPhone 4, The latency is, for the acquisition part, around 17 milliseconds, and for the rendering, around 20-odd milliseconds. So you have really around about ballpark of about 10 milliseconds to really make this real time. Now, what they do in augmented reality, for the most part today, what you see is marker-based augmented reality. So they simplified the issue of what you're detecting. You basically put a known object in the environment, a marker, as you can see here in the diagram with the question mark over it. So the camera is actually looking for that predefined marker. It's got corners on it, so you know exactly the orientation of that marker, and then you can paint some graphic on top of that marker. So doing it this way, augmented reality based on markers, simplifies the processing significantly, and thereby you can come out with this sort of first version of augmented reality based on the markers. But really the marker-based approach is really using very simple computer vision processing functions and in order to determine the pose of the camera and to paint the graphic where you want it. So if you look at processing loads, though, for, say, typical smartphones that are out there, they're doing, basically on the frame sizes there, you can see everything from QVJ up to a megapixel, the iPhone 4G with a megapixel. The processing time to do detection and tracking on the device, which, like I said, has to be below 10 milliseconds to make it real time from the time you do the acquisition to the time you get it on the display. These phones with very high performance applications processors in them are clearly not real time. The detection function is much greater than 10 milliseconds. In the case of the iPhone 4G, which is trying to process a megapixel of real-time video data, it's at 182 milliseconds. So far from actually being useful for doing real-time marker-based augmented reality, interestingly enough. So you need actually something that's much better. To give you an example, the core that we developed, Cognivue's developed a massively parallel vision processing core. I don't want to do an advertisement for Cognivue here, but our vision processing core, which goes inside the chip, the second generation core is the one that semiconductor companies are licensing from us now, at 600 megahertz will do that same processing in less than 2 milliseconds on a megapixel of data and in the milliwatts range. So the next challenge, of course, is really to make augmented reality or the ability to detect and classify objects in real time without markers, okay, where you're actually, you got a device like a smartwatch or a pair of glasses or even a smart pen, where it's actually got, it's not looking for markers, it's actually trying to detect objects and classify them in real time. That's called markerless augmented reality. And it's really what you need, to make it augmented reality useful in sort of outdoor situations or to detect any sort of feature or object that you want to pick up. The key with augmented reality that's markerless based is you got to have some way to actually determine where the camera is in the real world, and that's called it's really you have to do this visual tracking and pose estimation to figure out that how the camera is orientated relative to the features that it's detecting. To do that, you can use sensors. Actually, the camera can figure out where exactly it is in the world through other types of sensors you might have in your device, like a smartphone. But more than likely, it's going to use what's called natural feature tracking, which is basically you're actually picking up features in the real world, tracking those features in order to determine the pose of the camera. So this particular sequence of vision processing is required is actually very complex and performance intensive. So the steps involved in natural feature tracking are this key point detection, feature extraction, feature matching, and the major algorithms that are used in the point detectors or the feature detectors, you have algorithms like good features to track and FAST and Harris corner detector. Today, commonly an application processor in a smartphone, if it's doing this particular vision function, it will be using FAST because it's considered to be the least performance or intensive. But it's not actually very accurate or precise. So in actual fact, you need to go to something a little bit more powerful or more precise, I should say, and that's, for instance, a feature detector like good features to track. The next hardest part in the pipeline, and actually the most hardest part of the processing pipeline, is what's called feature descriptors. And these are algorithms. Some of them are patented, some aren't, but SIFT, SIRF, as examples, are feature descriptors. And then you have to do pose estimation, which is the least performance intensive. So looking at SIFT, because it's the most difficult algorithm to do, this is actually a feature descriptor. Again, looking at the performance of SIFT, the algorithm, which does the description of the features that you're trying to detect, the processing on these various iPads and iPhones, and as well on applications processors for that use GPU and CPU together, like Qualcomm Snapdragon, as an example. The process delay is shown there again in milliseconds. Again, not sufficient to do real-time natural feature tracking. If SIFT is taking this much time to do, you certainly can't do real-time natural feature tracking. You certainly can't do Markerless-based augmented reality real-time with anything that's actually on the market today, for sure. You're orders of magnitude away from actually having sufficient performance. Somewhere in the ballpark of about 5 to 10x performance improvement over existing high-performance GPUs. Our technology, our first generation or second generation version of our processor core actually is today, if you design a chip with the core, you can do this feature description for real-time augmented reality or Markerless-based augmented reality in sufficiently low enough process time. And actual fact, our third generation, which is significantly about four times better than that, actually can do it significantly faster. So it makes it possible in future products, not far away, I'm saying about 3 years when these chips come out, you'll be able to do this Markerless-based augmented reality in portable devices. So, and the last thing, actually, this is just showing another example, but there are companies out there that have tried to optimize the algorithms that are used today, and they've gotten about a 10x improvement on, for instance, HOG performance. HOG is another feature descriptor, and they've managed to get it down to the range where maybe you could do it real time, but it's still quite a ways off. Again, if they had a vision-specific processor core in the chip, or they were using, they could actually do this sort of sophisticated feature detection feature detection and description with an Apex core. So the architectural implications, really real-time performance. You need 50 milliseconds across the board to actually go from acquisition to display of an object. You need to actually to do that entire pipeline of processing in less than 10 milliseconds, and really to allow for low power operation, probably less than 5 milliseconds. Natural feature tracking, which is the thing that you have to do in order to do this Markerless-based augmented reality, really needs about 100 times more performance in processors today in order to make this a reality in devices, especially if you're trying to do 1 megapixel or more in resolution. And of course, you have to focus on not just getting the performance in there, but doing it cost effectively. So our technology basically solves this problem, and you'll actually see the first generation version of our technology in products like this Smart Pen, but also cars that are coming out this year and next year actually are using a first generation version of our vision processor for doing detection of objects as you're driving. So this is just an example of a connected device. The Smart Pen here, which is by a company called Neolabs, just went into production. And it's got a camera in the tip of the pen. It operates on a battery for more than a week. It operates at 120 frames a second. And if you want to come up and try it out, you can see it. But it's basically designed to, you can write on a piece of paper, sketch, draw, whatever it is, and it actually will instantly transcribe it to your whatever you're writing, regardless whether it's text or drawings. It will instantly transcribe it to your smartphone, tablet, or to a network server, or it can store up to 1,000 pages of whatever you happen to be writing. So it's an interesting application of vision technology that's only realizable because it actually can be done at a low enough power level and a small enough size, and that's as a result of the first generation version of a vision core that's in there. The same technology, though, that you see in some of these consumer devices are actually be in the cars you're driving in the next couple of years. Thank you.
Thanks very much, Simon. That was great. We're running a little bit out of time, so if you have any questions, please approach Simon, and we're going to be heading towards our next session in just about 5-7 minutes. Thanks very much.